Oh, let me share my screen. So again, we already gone through fundamental concept, we already gone through stiffness displacement method. Now we're going to look at thrust equation, and then I'll give you assignment after this. Yeah. So we're going to look at development of thrust of equation today. So for chapter 3, we're going to look at 3 things. So we're going to look at displacement function for bar element. And then we're going to look at what is transformation of vector, and also how to find stress, And then, yeah, and then we're going to look at plane thrust scenario. Okay, now what I'm trying to do now is we're going to derive a stiffness matrix for bar or thrust element. And our bar behave linear elastic, which means that our bar behave within the elastic region. So we're going to introduce you to another new dimension. Previously, we looked at local coordinate. Now we're going to look at global coordinate. Previously, in chapter 2, we only looked at local coordinate. Now today, in chapter 3, we're going to look at a global coordinate system, and then we try to relate what is local, what is global. Yeah. Okay. So what is thrust? What is plane thrust, or what is the word thrust? Is the word you see on the screen now. Thrust is a structure that support loading, either on the top or bottom. That you'll see there's a body of structures that handle the loading, distribute the loading to all the body of the structure here. Let's jump into the derivation. So in your chapter 3 tutorial question number 1, you will see the same diagram. So what does this diagram mean? You have a bar and the length is L. At this bar, you have point number 1 and point number 2. And there's a force pulling the bar at both ends. Alphabet T to represent tensile loading. Tensile means you're pulling from both ends. If you look at C, means capital C is a compression stress. Compression loading means the arrow will go in both sides. Yeah. So again, with the L, big L is the length between point 1 and point 2, or both ends of the bar element. There's a loading on both ends. In this case, you have a tensile loading. And you have x direction, and the displacement is in u is the displacement in the x direction. So you have point 1 displacement, local force at point number 1. Same with point number 2, you have u2 displacement at number 2, point number 2, and the local force at point number 2 in x direction. So these are all the general notation for the diagram. Yeah. So, okay. There are some refreshment for all the mechanical property. For example, modulus of elasticity, E modulus Young. Yeah. And so on. And this bar having a constant cross-section area. Yeah. What else? So this bar, we are having a 2 degree of freedom, meaning we have a displacement at point number 1 and point number 2. So these 2 points are free to move in x direction. So we have 2 degree of freedom. What else? Okay, we need to recall back what we learned for our strength displacement relationship. So definition of modulus Young is the ratio of stress versus over strain. So if you rewrite the equation for your stress and strain, so stress equal to modulus Young or constant value of your elasticity times the strain. Okay, so this one you should recall back. What is stress? What is strain? Yeah. Okay, just a recap. So again, if you have a cylinder body, this is the area. If you have a force perpendicular to the area, this one will generate normal stress. You take the force, because this is normal, and divided by area. This is the area, right? Becomes stress. So if you have another force, let's go this way. If your force, tangential force, parallel to the area, then this action will generate shear stress. Shear stress, tangential divided by area. Yeah. So these are the effect of cause and effect of your force and area between the relationship between your force and area. You will generate normal stress and shear stress. And if the object elongate, let's say your object elongate after pulling, so let's say this is original length, and there's a displacement or there's an elongation, delta L, then your strain will be the change of length divided by original length. So this is the fundamental, and you link modulus Young with stress and strain. That's why you get this equation. Yeah. So this one you learn in other module in your static and dynamic class. Right. So again, strain is the change of displacement. In this module, chapter 3, we use U to represent the change of length. In this case, we name it as displacement. The U over the X means the change of displacement in X direction. So this is the mathematical model we use for strain. Yeah? And force equilibrium, what we use in this case is tensile force, tensile stress. Tensile stress, this is a stress, right? Tensile stress. T, tensile stress. All right. In other module, you see this symbol with a T. In this case, because we are referring to the diagram, so straight away use capital T as a stress. So you know that stress equal to force divided by area. So you want to find the force. So this is a tensile force. Sorry, yeah. Just now I mentioned this one stress. So what you do is you rearrange the equation. Yeah. So your force equal to stress times A. So this is a force. Tensile loading. Tensile loading. Force T because it's stretched to both ends. So T is a force. Tensile force equal to area. Area is the cross-section area of this one. So cross-section area, it can be many cross-section. You can have cylindrical, you can have I-beam, you can have this one, rectangular beam, and square beam. Yeah, so these are the area, cross-section area, times the stress in x direction. So this t value is a constant. So we pull the diagram and the equation together. So we have the diagram, a bar diagram with the displacement and the forces at both ends. And the first equation is the stress-strain equation. Second one is the strain, definition of strain. And the third one is the force equation, relation with the area times the stress. So these are the three equations so far. You combine these three, you rewrite in a force dimension. Tensile force equal force, your F, right? Your tensile force equal to AE du dx. You rewrite, you substitute inside this equation, right? Your stress in x direction equal to modulus Young, modulus of velocity times the shear. So this one, strain equal to du over dx. Again, u here is the displacement. So you substitute this one in and you put this one in here, you'll get this one. Okay. Then we try to use the differentiation. We try to develop a differential equation. So we will have this one. We take our force equation and then we differentiate it in x direction. And because our material is linear elastic, which means the difference of our force here will be constant, will be zero. So this mathematical model, if you write d over dx something equal to 0, means there's a steady state. We have a steady state behavior. In this case, we have a linear elastic bar that under the force, the tensile force here, is a constant under a constant value. Yeah. So three equation you combine, you get force. So you differentiate the change of force in x direction is constant. You put equals 0, then we get a differential equation. Yeah. Again, the concept is to mathematically we write the way you pull the force at the constant rate. Yeah? As a constant rate. So d over dx means the change of this component is force. It is your t. The change of force in x direction equals 0. So it means you have a steady state here. You're pulling the force at the constant rate. Yeah? All right. Now we have a few assumptions when we derive the differential, when we derive the bar element stiffness matrix. First one, the bar do not have shear force or bending moment. Yeah. Again, the assumption, when we pull this bar, the bar do not have shear force. So there's no shear force effect, or there's no bending moment, because in real case, you pull a bar, steel bar, you pull, the bar might bend over due to the material property itself. So the first assumption here, our bar here do not sustain or do not behave any effect of a shear force. So we don't have F1y equal to 0, means that in here we don't have any force here. We don't have 1y here. Y, if we have this one, then we have a moment, a bending moment, yeah, a bending moment. Okay. Again, the definition for moment, still back to your physics. What mean by moment or torque? So if you have force and you refer to a point, it must be 90 degree. This is t distance. So you want to create a moment m at this point a. So moment at a equal to force times t. This is moment, and the relationship between force and distance must be, and the surface or the point must be 90 degree. Then you get a moment. Okay, so that's why we assume that we don't have y component at point number 1. Same with 2 also, we don't have f2y also. And yeah, moment at 1 and 2 also 0, yeah. Moment at 1 and 2 is 0. Assumption number 2, we ignore any transverse displacement. Means if you pull in a realistic case on the bar, some portion will move very fast, some portion will move very, very slow. Yeah. So especially if you pull at this end, some material will displace or faster. Yeah. So we don't have that effect in this assumption. And Hooke's law apply. What is Hooke's law? F equal to kx. Hooke's law, this means spring. Law apply. If you pull a spring and this spring displaced with x, with F, then this effect will cause you the spring force, yeah, spring force with a K. So you have a spring force there. Okay, Hooke's law, basically this equation. So again, in exam, if you need to use Hooke's law, you write this equation, you get 1 mark now. Okay, so just for info. Yeah, so another one is that there's no intermediate apply force. The force do not you do not apply the loading in a certain way. Yeah? Okay, we go a bit faster. So there are 7 steps to derive the stiffness matrix for bar. Okay, in your tutorial is below your question 1. So there are 7 steps. Step 1, select element type. Select an element type. So again, what mean by element type? You have 2 node element. You have 3 node element. You have more than 3 node element. You have 3-dimensional element. Yeah, and you have symmetrical element. Okay, so if you cut across this cylinder, you have a symmetrical body, a square cylindrical square body. So this one you choose your case. Yeah, so the first one you select element type. All right, the second one you choose the equation for displacement. Yeah, so there's an equation for different type of displacement. So if you have a spring behavior, normally we will skip step number 2. Yeah. So means that function, you know the equation, you have linear equation. If you plot graph, y versus x linear, you have a line. You have y equal to mx plus c, which is a linear equation. You have quadratic. You have a curve like that. You have 8y equal to x squared plus bx plus c. You have polynomial, meaning that the n here is more than 2. it means something like axn plus bx n so on, yeah, n minus 1 plus c x n minus 2 plus. This is a polynomial general equation. Yeah? So if you do not know what is polynomial, again, go back to your calculus or advanced mathematics. Go and find what is polynomial. Yeah, example is that you have 4x3 plus 2x squared plus 1, for example. This is polynomial because the index here is more than 2, right? 4 under cubic. Yeah, but you know that our bar element just now, bar element, we in our assumption we assume that our bar is like a spring, so Hooke's law apply. So F equal to kx, and you look at this form, this is a linear equation, right? F equal to kx in the form of y equal to mx plus c. So your c is 0, your m is k, your y is f. So this is a linear equation. So for this chapter 3, when you deal with bar, step number 2, you can straight away skip because we know that we are using Hooke's law. Yeah. Although the word skip here means you already know the function that you use for displacement, you're going to use Hooke's law, F equal to kx. Yeah. Step number 3, you define the strain stress displacement and relationship. Yeah. So this is number 3. Later we look at one example, how we do it. Yeah. So the first equation for step number 3 is strain. What is strain? Strain actually is the change of length divided by original length. So in this case, because we already defined with this diagram, our displacement, you take the displacement at point number 2 minus displacement at point number 1, you get the delta L. Yeah, again, don't confuse with the U in the physics. In this case, U is a displacement, it's not a velocity. So don't confuse with the notation. Yeah. So U2 minus U1 is the change of L. Again, in exam, don't write something that we don't cover in lecture. Write something that we already discussed in lecture. Yeah. So in exam, don't write delta L equal to something. I'll put a question mark. What is delta L? Yeah. So all this will from your free body diagram. Another one is your modulus Young equation. Stress equal to modulus Young times the strain. So these are the two equations that we're going to use many times. For example, in chapter 2, you see F equal to KD. In this chapter, you will see a lot of times strain and stress equation. Then, because we have 7 steps, step number 4, you derive the Stiffener matrix. All right. So these are the equation. So in this case, your f1x, which is at this point, equal to negative t. We already see this one in chapter 2 already. We already derived the Stiffener matrix for spring already. So this one is just a refresh. Yeah? So t is to the left. That's why you get a negative here. Because all our x direction is positive. To the right is positive. So your t to the left, that's why you get negative here. And we already define what is our tensile force here, equal to AE times our strain. Same with point number 2, F2x equal to T, and right again in the term of AE and displacement. Yeah. So F2x equal to AE, U2 negative U1 L. So one with the negative, one with the positive. Yeah. Different point, different value. Once you have this set of equation, you put in the matrix form. Okay, you put in the matrix form. So these two, you put in a matrix form. F 1x, 1x, 2x on the left hand side. Then you know that your matrix equal to F equal to KD. Again, we are looking at an element, so that's why you use a small f here. So your K is your AE component divided by L component. Yeah. Okay, how you derive this one already explained in chapter 2. How we get this one. Go back and refresh how we get the K minus K. So actually is an equation that we derive. So for example, the first one, f1x equal to negative AE U2 divided by L minus minus positive AE U1L. So we want to put in U1 and U2 form. That's why we write AE U1 and L negative AE U2L. This is for F1x. And then F2x, you repeat. F2x equal, you break U2 divided by L minus AE U1L. Because we start with the U1, so you rearrange the equation for F2x. So we get negative AE U1 divided by L plus AE U2L. So we have the first these two equations. We transform these two into matrix form. Okay. So how you write matrix form? F1x equal AE times U1 plus negative AEL divided by U2. So you transform these two equations into a matrix form. Then from here, if you make direct comparison, F equal to KD, our K, this is our K. So you can write our stiffness matrix K equal to AE divided by L, 1 minus 1 minus 1, 1. Okay. So for chapter 3, when we look at bar, we will no longer apply what we learned in chapter 2. With chapter 2, you see the K value alone. This is chapter 2. However, when you come to chapter 3, because you are looking at bar, your bar, because it's behave like we are using elasticity law, we are using stress and strain combined with the elasticity that parameter, our K become this form, AE divided by L, and we have a symmetry matrix here. 1, negative 1, negative 1, and 1. Okay, so this is the step number 4. Number 5, you put everything in global, means you combine what we did, the superimpose that I discussed, that we discussed just now in chapter 2, your question number 11. You superimpose all the metrics together, put into their location. You solve for the unknown. The first one, you solve for the displacement, you solve for the force. Yeah. So basically, you start with the matrix equation. Start with the equation F equal to KD element. Then you put into global dimension. Then you solve for displacement. After that, you solve for the force. Yeah. So what is added from chapter 2 is that we are pulling in the definition of stress and strain. Again, stress and strain relationship is this one. Stress equal to modulus Young strain. And then recall what is strain. Strain is a change of, again, change of L over L for this module, because we are referring to this diagram. So our equation will be U2 minus U1 over L. We put in here, then we'll get this one. Okay, we'll get this one. So these are the 7 steps for chapter 3. Yeah, let me see the time. Okay, I think I need to let you go because almost 10 o'clock. We have another class. So again, we stop here for chapter 3. At least today we cover the 7 steps. Yeah. Okay. Okay, let me stop the recording.